Alright, so in today's tutorial video, we want to look at statistical methods for analyzing three or more independent samples, also known as analysis of variance in R. But before we proceed, I'll urge you to kindly take a look at my previous tutorial video on the flowchart for classifying data, because in that video tutorial, I have illustrated and explained the data structure for three or more independent samples, which will help you to catch up with everything that I'm going to do in today's tutorial video, okay? So you can just click on the link in the card above or check the description of this video for the link. Alright, so one thing with regards to ANOVA is that it is one of the most flexible and practical techniques for comparing several means compared to the two sample t-test, okay? And it is important to note that ANOVA is not about analyzing the population variance. However, the basic principle of ANOVA is to test for differences among the means of three or more independent samples by examining the amount of variation within each of these samples relative to the amount of variation between the samples, right? So the types of ANOVA include the one-way ANOVA, also known as the completely randomized design. We also have the two-way ANOVA with no interaction effect, also known as the randomized block design, RBD. And we have the two-way ANOVA with interaction effect, also known as the two-way factorial design. In today's tutorial, we are just going to cover the CRD and the RBD, okay? The two-way ANOVA with interaction effect will be covered in our subsequent tutorials. Alright, so like the two samples for the two independent samples, we have parametric tests and non-parametric tests for analyzing such data. The same applies with having more than two independent samples or three or more independent samples. So the type of parametric test for three or more independent samples is known as the one-way ANOVA. This model compares the means of three or more groups to determine whether there is statistical evidence that the associated population means are significantly different. For example, researchers might want to compare the mean income level of three regions, or researchers might want to compare the mean nitrogen content of 4 lakes, or researchers might want to compare the mean effectiveness of 5 drugs, okay? So there are certain assumptions which must be satisfied before this test can be used. One of the assumptions is that the groups or samples are independent. The next assumption is that the response variable is continuous. And the next one is that the data follow the normal probability distribution, and also the variances of the samples are equal, okay? Now let's take a look at the non-parametric test for three or more independent samples. This is known as the Kruskal-Wallis test. This test compares the medians of three or more groups to determine whether there is a statistical evidence that the associated population medians are significantly different. So, for example, researchers might want to compare the median income level of three regions, or the median nitrogen content of 4 lakes, or they might want to compare the median effectiveness of 5 drugs. So there are certain assumptions which must be satisfied before this test can also be used. One of the conditions is that the groups or samples are independent. The next one is that the response variable is continuous, and also the data does not follow the normal probability distribution. And the last one is that all groups have identical shape distributions, okay? Alright, so now let's take an example. A betting company has introduced a new gaming policy in 4 countries, namely A, B, C, and D. The betting company randomly selected 5 areas in each country and recorded its daily income in dollars at each selected area. The dataset is shown in the attached bet dataset. The betting company wishes to determine if there's any significant difference in the average income among the countries. We want to conduct a detailed statistical analysis for this problem in R. But before we jump into R, let's take a look at the bet dataset in a CSV format. So here we go, we have 3 variables. We have country, area, and income. Income is continuous, whilst the first 2 variables are categorical in nature, right? So we want to find out how this income for the first country differs from the income for the second country. This for B, and this is the income for the third country, right? And this is the income for the fourth country. We want to see how this income differs among these countries, right? But there's another variable known as area, okay? And this area variable can have influence on our income. For example, if the betting company is located in an area where most of the youth don't have interest in betting, then definitely the income level will be different compared to an area where most of the youth have, or where most of the youth have interest in birthing. Okay, so in design of experiment, if you have a variable that you think will have influence on your response variable, but that variable is not of primary interest, then that variable becomes a nuisance variable. And in design of experiment, one way to deal with nuisance variable, if this variable is known and it can be controlled, is to use the blocking principle. In blocking, um, blocking basically refers to a process of grouping the similar experimental unit together into blocks in such a way that the units within each block are more or less homogeneous. So if we are going to use this as a block, then this for country A, this will be at a block. For country B, this will serve as a block, and for country C, this also serve as a block in that order. Okay, this also serve as a block for country D. Right, and this will be for the second one in that order. Right. So in using the blocking principle, um, one assumption is that there's no interaction between this and that. There's no interaction between these two factors. We just want to observe the effect of this on the response and the effect of this variable also and on the response. But there's no interaction between these two variables. In the case where we want to assume that there's interaction between these two factors at the same time, these factors also have some effect on the response, then we are going to make use of a two-way factorial design, but that one will be covered in our subsequent tutorial. Okay, so with a blocking principle, there's no interaction between these two, right? But we just want to observe the effect of this on that and the effect of this on that. Okay, so that's basically what we're going to do. So in today's tutorial, we are just going to cover the one way ANOVA, where we want to find out how the income vary among the countries, and also employ the randomized block design by trying to control the source of variability that may come from this variable area. Okay, because once we have this variable in as part of this data set, it may have influence on our response, and we would like to control it. So the best way to control is to make use of the blocking principle. Okay, and that's where the randomized block design comes in. So we'll be looking at the parametric version of it and the non-parametric version of it. Okay, so now let's jump into our studio. So the first thing that we want to do is to clear all our environment and graphic windows. If you have yours clean as mine, you can just skip this line and just proceed to import your data set. So I want to import my data set. I want to assign my data set to Bert. So I'm going to use this code of line to do that. read.csv file.choose. Okay, so let me run this. Alright, so I'm going to leave this data file in the description of this video so that you can download it. Okay, so I'm going to open it. Alright, so once you import your data set, you have an information environment window. You can just run this to view your data set, or I can also click on this to view my data set in a spreadsheet form. So I'm going to click on this. So here we go. Okay, the next thing I want to do is to look at the structure of my data set. So control enter. So we can see that country and area, they are characters, but income is numeric, which is quite good. But we don't need characters, otherwise we have some challenges in our computation. So in our data manipulation, we are going to encode these two variables and convert them into a factor, because these are categorical in nature. Okay, so that's basically what we're going to do. In R, we need a library to help us do the data manipulation, and the dplyr library is very vital for that. So I'm going to run this, control enter. If you don't have this installed, you can go to packages and click on install, type the name, and make sure that you're connected to the internet to install. Okay, alright, so once we load this library, we want to recode the country and area into factors. So I'm going to assign my data set to new dat. So I'm using the mutate function, which is going to add another variable to my current data set. So I want to convert the previous variable country into a factor, but I want to give it a new name, country, with small c, and the area is also going to be a factor, but I'm changing the name to small a. Okay, I don't want to override the previous one. So let's run this, control enter. So I can click on this to view my data set. Here we go. So I have two other variables which have been added. So these are now factors, right? But these are in characters, so I can remove this and maintain this. So let's go back to our script file. So if you look at the structure of the new data set, you can see that country is now a factor with 4 levels, and an area is also a factor with 5 levels, so we are good to go. So the next thing that we want to do is optional, is to remove and rename our variables. Okay, this is optional. So I want to remove the country and area, which is in characters, and to rename my income as income with the initial starting to be a small letter I. Okay, control enter. So let's see the structure now. So I now have 3. If I click on this, I have only 3 variables again. Okay, so we are good to go. Alright, so the next thing that I want to do is to basically attach, this is also optional, is to make the variables accessible in R. Okay, alright. Then the next thing is to now determine how income vary among the countries. So we want to start with the one we are over. But before that, we have to do some experiential analysis. We have to at least get to know the mean, right, of the income across the countries. Okay, and as well as the standard deviation. So we want to start with some quick data summarization. We want to get a mean and standard deviation of the income for each country. Okay, so with this code of line, I'm going to get my result. Control enter. So I have the income for the mean income for the first country, right? A, B, C, and D with the corresponding standard deviation. Now if you look at this mean values, you can see that we will not be we wouldn't be surprised if we end up having some significant difference, because if you look at the country A mean income compared to country D mean income, you can see that there's some clear difference. Okay, 17.3, 25.4. Even if you compare that of B and D, you can also see some clear difference, right? So at the end of the day, in our ANOVA analysis of variance, we shouldn't be surprised if we end up having some clear difference. Okay, based on what you have observed here, we are likely to see some significant difference at the end of the day. Okay, we can also visualize our income distribution by country using the box plot. So let me highlight this. With this code of line, I'm going to get my result. Control enter. So here we go. So we can see for country A, we have some extreme value, right, which seems to be an outlier. And for country B, the distribution seems to be symmetric, right? For country C, the distribution of the income also seems to be symmetric. For country D, the distribution of the income also seems to be symmetric, but the area at the lower half of the median is more than the area at the upper half of the median. Okay, alright, so let's proceed now to fit the one-way ANOVA model. We want to do this so that we can basically use this to test for the assumptions. Okay, so let's run this. Control enter. Alright, so with assumptions, we can see that actually these groups are independent, right? You can see country A is different from country B, and country B is also different from country C, and it's also different from country D. So these are totally independent, and for each country we have different areas, so definitely these variables are, or groups are independent. Okay, so the next assumption was that the response variable must be continuous, and you can see that this is continuous. So the next assumption is to test if the data is normally distributed, and we are going to make use of the residuals, which is basically the difference between the actual and the estimated value. Okay, so we want to start with a QQ plot. This is for the normality test. Okay, so with a QQ norm, I'm going to make use of the residuals for my fitted value, which is the difference between the actual and estimated value, and I want to give it a color of blue. I want to give it a line, the QQ line, to help me to know if the points are going to be on the straight line sloping upwards to the right. Okay, so control enter. So in here we can see that most of the points are on the straight line sloping upwards to the right, which is an indication that the distribution of the income, right, among the countries is normally distributed. Okay, Another way to test for the normality test is to make use of the Shapiro-Wilk test or the Anderson-Darling test. For Anderson-Darling test, we need a library known as the node test library. So let's quickly run this. Control Enter. So let's start with the Shapiro-Wilk test. Control Enter. We are still making use of the residuals. Now comparing this p-value to the alpha level at 5%, it means that we are failing to reject the null hypothesis and conclude that there's enough evidence to indicate that the distribution of the income among the countries is normally distributed. Okay, let's take a look at the Anderson-Darling test. Control Enter. Also comparing this p-value to the alpha level at 5%, it means that there's enough evidence to indicate that the distribution of the income across the countries is normally distributed. Okay. Alright, so I think we are good to go. Now the next assumption is to test for homogeneity of variance, and we are going to make use of the Bartlett's test. Okay. Yeah, the null hypothesis is that the variation of the income among the countries are the same. Okay. So let's quickly run this. Control Enter. So looking at this p-value compared to the alpha level at 5%, it means that we are failing to reject the null hypothesis and conclude that the variation of the income among the countries are the same. Okay. Alright, so now if this test of homogeneity of variance were to fail, we can still proceed and make use of the one-way ANOVA, but we are going to employ a different function to get a result. Okay. Alright, so another way to test for homogeneity of variance is to plot the fitted values against the residual values. Okay, so let me run this. Control Enter. In here we don't see any correlation between the residuals and the fitted value, so this is an indication that the variation, alright, of income among the countries are the same. Okay. Alright, so the next thing that I want to do is to summarize our result. We have all the assumptions for the parametric case has been satisfied, so we are going to make use of the one-way ANOVA. So we want to summarize our result. The null hypothesis is going to be that there's no difference in the mean income among the countries, and the alternative will be that the mean income differs for at least one country. Okay, so let's see the result. Let's get a summary of this fitted value. Control Enter. So if we look at the country, you can see that we have some significant difference, 0.005 compared to alpha level 5%. We are rejecting the null hypothesis and conclude that the mean income differs for at least one country. So the question is, which of these countries differs? We are going to look at it very soon. Okay. Now let's assume that there was no equal variance. Okay, the test of homogeneity of variance failed. Then we are going to make use of this to get the analysis of variance result. Okay, so let's run this. Control Enter. So also comparing the p-value, right, to the alpha level at 5%, we're also going to conclude that the mean income differs for at least one country, assuming that there was no the test of homogeneity of variance failed. Okay, or assuming that the variation of income in the among the countries were not the same. We're also going to end up concluding that the mean income differs for at least one country. Okay. Alright, so the next thing I want to do is to now determine which of these countries differs. Right, now we have evidence that the income level differs among the countries. So which of these countries differs? We want to do that. Multiple comparison test, assuming equal variance, and want to start with we want to basically start with assuming equal variance, right? So basically what I'm trying to say is here is that we want to get the multiple comparison test assuming equal variance, right? Then we also check the multiple comparison test assuming an equal variance. Okay, so assuming equal variance, we are going to make use of the TKHSD test, but we need a library. First we have to load this library. If you don't have this, you have to install before you can load. So let me run this. So let me run this to get a ticket test, which will help us to get a post-hoc test, or to help us to determine which of these groups differs. Control Enter. Now we can see from this p-value that country D and A, their income differs, right? The difference is significant. The same applies with that of country D and B. If you have to compare their mean income, the difference is also significant. So this is basically where the difference lies. So the difference basically lies between country D and A and country D and B. Their difference is actually different from zero. Okay, we can actually visualize this result by making use of this function or code of line. So once I run this, I can visualize this in this form. This is the plot. So we can see that if you are to look at the income for country D and A, you can see that the difference is quite far from zero. The same applies with that of country D and B. Okay. All right. So now let's get a multiple comparison test assuming an equal variance. Okay. So this is the code of line to get that result. So let me quickly run this. Control Enter. So here we go. So we can see that the difference lies between country A and D, 0.019 compared to alpha level at 5%, means that the difference is significant. The same applies with country B and D, 0.011 compared to alpha level at 5%. It means that there's a clear significant difference in the income level between these two countries. Okay. All right. So I think we are good to go now. So now let's assume the normality test failed. Okay. Once the normality test failed, then it means that we are going to resort to the nonparametric test and make use of the Kruskal-Wallis test. Okay. So the null hypothesis is going to be that let me check. The null hypothesis is going to be that there is no difference in the median income among the countries, and the alternative is going to be that the median income differs for at least one country. Okay. So this is the code of line to help us to get our results for the Kruskal-Wallis test. So Control Enter. So run the p-value, compare this p-value to alpha level at 5%. It means that we are going to reject the null hypothesis and conclude that the median, there's enough evidence to indicate that the median income differs for at least one country. So the question is, which country differs? So there's a way to also get the post hoc or the multiple comparison test for the parametric version by making use of this code of line. Okay. So the pairwise dot Wilcox test will also help us to determine where the difference lies between the countries. Okay. So Control Enter. And we can see in here that also the difference lies between country A and D, while their mean income is significantly different. The same applies with country B and D. If you look at the p-value 0.032 compared to alpha level at 5%, we are rejecting the null hypothesis and conclude that there's clear difference in the median income between these two countries. Okay. All right. So now the next thing I want to do is to basically assume income vary among countries and areas. Okay. So now we want to include this variable. We want to assume that this variable is not of interest but can have influence on our response variable, which is the income. Okay. So we want to control the source of variability that may come from here, and that's where we want to apply the blocking principle. Okay. So in here we are going to make use of the parametric version of it, which is the RBD, and the non-parametric version of it is going to be the Friedman test. Okay. So let's go back to our R studio. So the parametric test for the two ANOVA with no interaction effect, remember that there's no interaction between these two factors. Okay. There's no interaction between these two factors. So if we were to assume that area, right, this Newton variable is known, but it may have influence on our response. So we want to control the source of variability that may come from here. The parametric test for this test is the RBD, which is the Randomized Block Design. Okay. So this is going to be the code of line to help us get our result. Control Enter. Then we get a summary of this. Control Enter. So in here, even if we include area in the model, you can see that it is not quite significant. Okay. It is getting to significant, but it's not quite significant. So the difference still lies in the country. Okay. So if you look at the p-value for the country 0.0017 compared to the alpha level at 5%, it means that we are going to reject the null hypothesis and conclude that the income level differs among the countries, okay? But if you are to consider area, there's no clear difference in the right. There's no clear difference in the income level among the areas compared to countries, okay? Now, the non-parametric version for the RBD is the Friedman test, okay? So the Friedman test is the non-parametric version for the randomized block design. That's the two ANOVA written interaction effect, okay? So in here, we are using area as a block, okay? So let's quickly run this to see the effect. So if you have to compare this p-value to the alpha level at 5%, you're also going to end up basically concluding that um, there's there's enough evidence to indicate that the median income level differs for at least one country, assuming that we use area as a block. Okay, so this is basically how to actually conduct a detailed statistical analysis for 3 or more independent samples in